So today's activity is based on the limits of resolution. So the resolution is the distance at which a lens can barely distinguish between two separate objects. So let's say you're looking at two dots in the distance. Can you tell if it's two dots or does it just look like one? So the resolution is limited by aberration in the lenses and also by diffraction. Although you can try to make a lens as perfect as possible so that you can limit the aberration, diffraction is unavoidable because it's due to the size of the lens compared to the wavelength of the light. So if you remember, we learned for single slit diffraction that when light goes through an opening, it spreads out and it has a minimum at a certain distance away. If it's a circular opening with a diameter d, the width of the central maximum from the center out to the edge is 1.22 lambda over d, and that angle is in radians. So the Rayleigh criterion for resolution is that, let's imagine that you have two objects, so you can see them over there on the left hand side. They're distance s apart, and you're looking at them through the lens. So the light goes through the lens, it gets diffracted, and each object is going to make its own diffraction pattern. And so then the question is, how close can that distance s be so that the two peaks look like they're two separate peaks and not just one very broad peak? So you can tell that there's two objects there. So the Rayleigh criterion says that the two images are just resolvable when it's at the position shown, where the peak in one of the curves is just over the minimum in the other curve, so the angle that's subtended by it is just the distance from the center to the first minimum, so 1.22 lambda over d. So that's the minimum angular separation for them to be resolvable. We talk about the resolving power, which is the distance s between the two, and that distance s is just equal to r times theta, if you remember arc length calculation. So theta times r, where theta is 1.22 lambda over d, and r is how far away the objects are. So if it's a microscope, if you assume that the object is at the focal point of the microscope, that's what you usually do when you're looking at the object, then the resolving power will be the focal length times theta. So it's 1.22 lambda f over d, and typically for a microscope, the focal length is about half the diameter of the lens, and so that means that we can't resolve details in something we're looking at that are smaller than the wavelength being used. And so that limits how small of objects that you can see with an optical microscope. The human eye can resolve objects that are about a centimeter apart at a distance of 20 meters, so that's 60 or 70 feet away. Or if you're reading something in a book that you're holding at your near point, so about 25 centimeters from your eye, you can see things that are about 1/10 of a millimeter apart. So the useful magnification of a light microscope is then 500 times to 1,000 times if you combine the resolution of the human eye that's looking through the lens on the microscope. Another question is, what size of a TV screen do you really need? So you can get a 60-inch or 72-inch TV. For a 60-inch 1080p TV, the pixels are about a millimeter in size. And so if you're a foot away, you can see 1/10 of a millimeter. So you can see, if you're very close to the screen, you can see the picture broken up into all the little individual squares, which doesn't look very great. You actually need to sit about 8 feet away in order for you not to be able to be bothered by the size of the pixels. So let's figure out what's the angular resolution of a human eye where the pupil is about 4 millimeters across, and the Southern Observatory Telescope, which is a very huge telescope, which has a diameter of lens of 8.2 meters for red light, so 660 nanometer light. So for the eye, remember the angle is 1.22 lambda over d. So my lambda is 660 nanometers. So that's 660 times 10 to the minus 9 meters. The diameter of the pupil is 4 millimeters, 4 times 10 to the minus 3 meters. And so I get an angular resolution of 2 times 10 to the minus 4 radians. That's a pretty small angle. How about the telescope? Well, the telescope, we got the same wavelength of light, but now the diameter of the lens is much, much bigger. Now it's 8.2 meters. And so the angular resolution is much better. It's 9.8 times 10 to the minus 8 radians. And of course, if we're looking at things that are very, very far away out in space, a very small angle can mean a big actual distance apart. So for the eye at 20 meters, so it's about 70 feet away, S, which is theta times R, take the angle, 2 times 10 to the minus 4 radians, times 20 meters, and we get 0.004 meters for a perfect eye, so that would be 4 millimeters. For the telescope at 100 kilometers, which is about the edge of space, S equals theta R is 0.01 meter, so it's about 1 centimeter. So if you had a telescope that had a lens with that size aperture on it, 8.2 meters, that was orbiting out in space, it would be able to distinguish objects that were about 1 centimeter apart. So the problem that you have to do today is this one. So if you buy yourself a 72-inch TV, and let's say it's a 720p, so 720p TV has 1280 pixels across its width. And we're going to assume, I know 72 inches on the diameter, let's assume that 72 inches across. And in that distance, you have 1280 pixels. Okay, so the first thing you have to do is figure out how wide is 1 pixel on the TV in meters. So you're going to have to convert that 72 inches into meters, and then figure out how wide each of those 1280 pixels is. And then once you know the pixel size, you know the S in the equation for the resolving power, and you're going to assume a green light in the middle of the spectrum, 510 nanometers, a pupil size of 4 millimeters. You can figure out your minimum angle. So now you have to figure out how far away from the TV do you need to sit. What's the minimum distance you need to sit away from the TV in order to be able to not see the individual pixel size.